Stuart, and let's welcome our next speaker, who is mengyuan Liu from China. And she's going to talk about the biological substrates of glucose metabolic covariance in the human brain. Welcome.
Good morning, everyone. Thanks so much for coming. My name is mengyuan Liu. So today, I'm going to share my research, which is unveiling the biological substrates of glucose metabolic covariance in human brain. I have no disclosures. So to start with, as we all know, glucose metabolism provides the energetic substrates necessary to sustain the neurodynamics that underlie brain functions. Studies have shown that the human brain consumes approximately 10 times more energy than would be expected based on its weight. However, recent findings indicate that the goal-directed cognition only consumes more than 5% metabolic cost compared to the resting state, which reveals the complexity of brain energy. One particular phenomenon is that glucose metabolism follows a distributed pattern across the brain, which manifests as a cross-subject metabolic covariation network, or we call it MCN. So this brings us to ask, what biological mechanisms underlie the glucose metabolism that supports neurodynamics? A logical starting point is that functional connectivity may be highly related to the MCN, as it reflects the temporal synchrony of both signals between brain regions. Indeed, previous research have shown that resting state functional connectivity co-varies with region glucose metabolism measured by FDG-PET, suggesting that regions with stronger functional integration tend to exhibit higher metabolic activity. In addition, structural connectivity may also play a role. Studies have revealed an overlap between SC and MCN, indicating that white matter fiber tree-based structural connectivity is a key substrate of FDG covariance. So this naturally leads to a broader question. Are there any other contributing factors beyond FC and SC? So we consider some different dimensions, like camel architecture, physical distance, etc. So to be more specific, we take structure covariance network, Euclidean distance, gene co-expression, receptor similarity into a multi-model framework to comprehensively investigate the biological substrates of metabolic covariation. So to achieve this, we used 45 patients with temporal lobe epilepsy undergoing pre-surgical evaluation, and we still have multi-model images, including 18F FIDG-PET, Hardy, resting state fMRI, and T1. They were all normalized to MNI space. So for gene and receptor data, we adopted from the Allen Human Brain Atlas and NeuroMaps respectively. Then we did the network reconstruction. A modified version of Lanson Atlas we used to isolate the brain into 121 regions of interest, from which we derived 6 biological networks. So these are the networks. Then we conducted a correlation analysis between the 6 factors and the MCN. After that, we also applied multiple linear regressions to evaluate the contributions of biological factors in shaping the MCN. Lastly, to identify which ages contribute most strongly to the similarity between each biological network and the MCN, we adopted the similar method of co-fluctuation time series. So for 2-region IMG, we use the product of the z-scores of 2 regions as the co-fluctuation value. So the high amplitude values represent the top contributing tiers. And similarly, we calculated the product of these scores across edges to identify those that contribute most to similarity between two networks, like for example, the FC and MCN. As for the results, the Pearson correlation analysis showed significant associations between all biological factors and the MCN. And the multiple linear regressions model accounted for a substantial portion of the variance in the MCN, with all predictors contributing significantly. And the VIFs were all below 2, indicating low multicollinearity. Now, for these ages, we examined the distributions of the top 0.5 contributing ages. And if you take a look at the pictures in the slide, you can find that as for the connections, the FC and the receptor primarily contributed to within network connections, while the Euclidean distance and gene predominantly contribute to between network connections. And apart from that, the SC and SN contributed equally to both within and between network connections. And despite the variety of in these spectral patterns, if you take a look at the right side of the slide, you could find that the default mode network, like in here, which is DMN, emerged as a frequently involved core network across all 6 factors. And apart from the DMN, as you can see, the second dominated networks in each factors are quite different. So moving forward, we still want to explore whether the factors have some overlapped ages. So we examined the shared contributed ages across different factors at multiple sparsity thresholds. As you can see, in the number of overlapped ages across factors increases with more liberal thresholds. But the convergence across all 6 factors remains extremely sparse, even at the top 10% level. So if you take a look at the first picture, there are only 1 overlapped age until we set the threshold at the top 10%, showing that the contributions of different factors are quite unique. So to sum up, we have two conclusions. The first is that at the global level, metabolic covariation network are shaped by multiple biological substrates, including genetic expression, chemical architecture, geometric proximity, cortical morphology, structural connection, and intrinsic neural activity. And second, by identifying age-level contributions and their corresponding core networks, we demonstrate that each biological factor uniquely contributes to the emergence of the MCN. So that's all for my speech, and I want to say thank you for your listening, and thanks to my supervisor, Xiaosong He, and my co-workers. So if you are interested in this, we have the poster here. Thank you.
Thank you. Wonderful talk. Very interesting.
Thank you.
I got a comment from the audience asking if we do still take oral questions. And yes, we do. So please feel free to come up to the mic, because now I'm taking you up to it, and ask your question there. It's really hard to see something from here.
Okay, given that there are so many different kinds of networks, why focus on the metabolic network as the output that you want to explain with the other types of networks?
Can you repeat that? I didn't catch clearly.
Why focus specifically on the metabolic network as the sort of outcome, as the end result?
Oh, just as I mentioned before, the metabolic, like glucose metabolism, is very significant to our brain energy consumption. And we think that these, like our brain cognition activities and the structure itself may have some relationships in the brains we consume. And we found that especially the cognition activities can't explain like all of the brain energy. So we really want to figure out what's the mechanism behind our like glucose metabolism.
Okay, so do you think this, it's more of interest to you than, say, other sort of commonly used ones like functional connectivity from bold signal? Or yeah, what do you think it can answer, questions you can answer with the metabolic network that you couldn't with other kinds of activity-derived networks?
Can you repeat it again? Because
like, as well, so the metabolic network is just less commonly used than a lot of ones like FC from fMRI data. So do you think there's, and in some ways it's harder to collect, harder to obtain? So do you think what do you think you can answer using the metabolic network? What questions do you think you can answer using the metabolic network that you couldn't from the usual sort of functional connectivity?
I'm so sorry, I'm going to interrupt here because for the sake of time, we have to move on. Maybe this is a question you can ask her later and kind of like discuss the specifics then. Thank you.
Thank you.